Welcome to this training session from Aerohive covering design scenarios. In this session we will be discussing coverage, user density, multicast in a Wi-Fi environment, challenging structural environments, and band steering. Coverage. A site survey should be considered mandatory. There are different types of site surveys, everything from a predictive coverage survey without ever physically visiting the site, to a coverage validation survey which includes a site visit, spectrum analysis, and even the old-fashioned walkthrough surveys. The predictive coverage survey uses software such as a topology map or the planner tool from Aerohive. If you've never conducted a predictive site survey, you can go to aerohive.com/planning tool and subscribe to a free use of the Aerohive online planning tool. Predictive coverage takes into account any free space path loss or obstructions that may be in between the access points and the clients which they are designed to service. Coverage for higher data rates should be somewhere at -67 dBm or stronger. Planning for voice should be at -67 dBm or stronger. Looking strictly at the numbers, they don't seem that far apart when you look at -70 versus -67. However, for every 3 dBm of gain, the signal strength is doubled, and for every 3 dBm of loss, the signal strength is divided by 2. So a -67 signal strength is actually twice as strong as a -70 signal. Looking at the diagram, you can see that this particular rendering was done for a signal strength of -67 dBm. Everywhere that you see at least the blue color, that is a -67 signal strength. As you move closer to the access points into the yellows and reds, the signal strength is even stronger. This is a predictive survey that was done for voice coverage. A very challenging environment is a classroom environment. Deploying in the educational vertical can be quite difficult because often the classrooms are separated by large cinder block walls. These cinder block or brick walls often have additional materials inside the brick as sound baffling to keep the noise down between the classrooms. If it is going to attenuate sound waves, it will also attenuate RF signals. Some school systems deploy one access point for every 1 or 2 classrooms just to penetrate the walls and provide the appropriate coverage. These materials can degrade a signal by 10 dB or more. A loss of 10 dB of signal strength is the equivalent of dividing the signal strength by 10. So if an access point is transmitting at 20 dB, on the other side of the wall, you're going to hear that at 10 milliwatts. A 20 dBm signal is equal to 100 milliwatts, but the attenuation of the wall would divide that by 10, making it a 10 milliwatt or a 10 dB signal. An average of 1 AP for every 2 classrooms can be needed for proper coverage, and even a greater density depending upon the walls could be needed to penetrate that, such as 1 AP per room. Other environments that are challenging may be challenging because of other noise in the airspace or so many devices and things contending for the medium, but this is strictly because of the attenuation of the partition types. Modeling for this in a predictive survey tool will greatly reduce the amount of time it takes you to do a physical survey. Once the APs have been deployed, you really need to do some type of coverage validation survey. Place an AP and walk through the environment using the same client devices and applications that the intended users are going to be using whenever that is possible. Doing a survey with a laptop when the clients are going to be using barcode scanners or other handheld devices such as phones is not an accurate measure of what the clients will hear. When you're deploying, it is important to try to match closely the power levels between the access points and the clients so you can have transmit and receive signal strength reciprocity. If you are trying to deploy for just RF coverage, do I have a signal in every corner of my building? Yes. Then you're going to wind up creating hidden node problems, near-far problems, devices that never really can contend for the medium with the other devices that are closer to the AP. So it's a good idea to do a valid walkthrough, and don't just plan for RF coverage, plan for what the devices need to do. A good RF design is designed around the intended use of the system along with the device types that the clients are going to be using. Wi-Fi deployments should never be about the shiny new buttons on the access points or some new feature you can do on the AP. It should always be about the needs of the client. 802.11 networks work at layer 1 and layer 2 of the Open System Interconnection or OSI model. If you're strictly doing a survey for a layer 2 analysis, you're missing part of the problems. Doing a survey for just layer 2 often involves scanning for other layer 2 devices in the airspace and trying not to deploy on the same frequencies as neighboring devices. That is part of a good deployment, but you should also know about non-802.11 noise sources that will cause true interference for your environment. That could be a microwave setup near the cafeteria. It could be 802.11 N or other devices that are taking up multiple channels if you're looking at it from a layer 2 perspective. But in layer 1, microwaves, cordless phones, baby monitors, Bluetooth, walkie-talkies, X10 cameras, there's a lot of devices that work in the same frequency range of 2.4 gigahertz, more so than work in 5 gigahertz, that are not 802.11 devices. Simply doing a layer 2 scan will miss all of this layer 1 interference. When an 802.11 device does a clear channel assessment to see if the medium is idle before transmitting, if it hears no 802.11 signaling but simply sees noise, it'll transmit and collide with the noise. Then when it does not receive an acknowledgement, it will have to retransmit, reducing throughput. Sometimes when you're deploying, you may have to switch your physical spectrum from 2.4 to 5 gigahertz, or from 5 gigahertz to 2.4, or from one channel to another, simply to avoid any layer 1 noise that could be creating a problem. And you are not going to find that simply by doing a layer 2 analysis. Spectrum analysis is vital to a properly deployed Wi-Fi environment. Band steering importance. Aerohive APs have the ability to encourage 802.11 clients to connect in 5 gigahertz if they have that capability, because 2.4 gigahertz is overcrowded with 802.11 devices and other noise sources. 5 gigahertz is much cleaner, although there are a few things that work in 5 gigahertz. There are not so many as working in 2.4. Multiple sources of interference in 2.4 are outside of the 802.11 world and would not be creating additional contention for the medium, but just completely disrupting it, raising the noise floor and reducing the signal to noise ratio, which would degrade performance. iPhones and iPods connect in 2.4. You may have also some Droid phones and other devices that only connect in 2.4, whereas PCs and iPad 2s and newer and MacBooks connect in 5 gigahertz. Which frequency range that the devices connect in is completely up to the client, much like roaming. However, when you implement Aerohive band steering, we will slow down the probe responses in 2.4, keeping the 5 gigahertz responses at a normal rate, thus encouraging the clients to connect to the cleaner 5 gigahertz. This is a screenshot of the configuration for band steering. The band steering is going to be applied to both the 2.4 and 5 gigahertz radios. When you enable the band steering of clients, you can choose the steering mode. It can be prefer 5 gigahertz or encourage. and then you can limit the number of probe responses per client as well. You could also choose band balance. With Aerohive 5.0 and newer, if you steer all of your clients to 5 gigahertz, 2.4 would then become the cleaner environment if you're not trying to avoid noise. So rather than just steering everyone into 5 gigahertz, you can also balance inside the bands so that we're steering to 5 gigahertz as much as possible, but also allowing clients to be in 2.4 as needed. You can also enable the steering of clients from 2.4 to 5 and choose Force 5. Then all the clients that are able to connect to 5 should try to connect in 5. However, since roaming and connectivity initiation are strictly up to the client, there's no guarantee that any one supplicant should be steered over. The attempt is to try to encourage them to connect in 5 gigahertz, but if a client absolutely wants to connect in 2.4 due to the configuration of that supplicant or the firmware in that particular chipset, then the client will still be allowed to connect in 2.4. User density. How many users should you allow per access point? It depends. How many devices do those users have? What is the intended use of those devices? It could be something as simple as data and just checking email or surfing the internet, or it could be something like streaming video or voice, which requires a lot of bandwidth. Email and simply browsing the internet are two things that don't take up a lot of bandwidth. However, watching streaming video or using voice over Wi-Fi are things that are going to take up a lot of bandwidth. So you need to know what types of clients and the intended use of those clients you're going to experience before you start deploying your access points. Are there going to be all laptops? Are you going to have something in a school system where maybe you have a bring your own device world plus some devices that are furnished for the attended students to use? So there could be a lot of devices total, but inside that it could be a smaller number of users than devices because each user may have multiple devices. When planning, you should look at the density of users and the density of devices as well, rather than just covering for the number of people and the square footage. Many educational systems have adopted what is being called a one-to-one deployment. Every teacher and student will have at least one device, MacBook or iPad, laptop of some type. The user density requires more access points. Since we're talking about a typical classroom with 25 or 30 students and the teacher, you're going to have that volume of users, and it's at least one-to-one. In some scenarios, it may be even more. You may have the students who have brought in their own phone, their own tablet device, and then they're using a laptop in class as well. So now those 25 to 30 students could possibly have 75 to 90 devices plus what the teacher has. At that point, if it's that high a density environment, you may need to look at providing at least one access point per room, and in auditoriums or gymnasiums where students congregate, maybe adding some more. The same would hold true for convention centers. Low user density classrooms, I might be able to get away with having one AP for every 2 classrooms. As you can see in this plan, the classroom that actually has the AP obviously will have a stronger signal, but by deploying the APs in this manner, you are able to gain signal in all the classrooms for a low density classroom environment. In that environment, you may get by with fewer APs because a large volume of APs may not necessarily be needed for proper coverage if you have a low density. In a higher density environment, you're going to need more APs, possibly one per room. By deploying them in the classrooms, you're more able to control the clients connecting at distance. By using them in the classroom, possibly using an integrated antenna version of a Hive AP, such as a 120 or a 330, and hanging that from the ceiling, then people farther away are less likely to be able to connect. If you deploy the APs right down the hallway, it's possible for people to connect at a greater distance and create near-far problems and hidden node problems, and you may create a situation where you spend most of your time troubleshooting, and the problem is you didn't do a great survey up front. So if you know you're going to be working in a high-density environment, plan for that and hang the appropriate number of access points to break up the collision domain, co-locating them properly on channels that are non-adjacent overlapping channels. And you may even consider implementing the high density settings in a Hive AP, as well as implementing band steering and band balancing. Load balancing is another technique that is designed to improve throughput in the Hive APs. For example, if I have 10 access points covering an office area, I don't want all of the users connecting to the same 2 or 3 access points. I'd like to spread that out to break up the collision domains. By enabling client load balancing among neighboring Hive members and choosing the load balancing mode properly, the APs are able to choose to ignore probe and association requests when a client is associated with another Hive AP until the anchor period elapses. And you can adjust this anchor period so that you don't have clients that are all congregating on one access point. By implementing load balancing, the Hive APs that have more clients connected are able to slow down their probe responses, where the clients are able to connect to APs with a lighter load, because the APs with a lighter load are keeping their probe responses at a normal rate. Multicast and Wi-Fi. Wi-Fi is a layer 2 environment. Once IP multicast traffic reaches layer 2, the traffic is no longer acknowledged because it is not a unicast transmission. Broadcast and multicast traffic does not have to be acknowledged in 802.11. Acknowledgement frames are used only for unicast frames. That way, if a single frame becomes corrupted or for some reason is not acknowledged, then you're going to have a retransmission. Multicast traffic must be sent at a lower data rate to aid in client reception at distance, because the client is not going to acknowledge that and let the transmitter know that it has received it. Push-to-talk features on voice over Wi-Fi phones often use multicast and will create a situation where you may need to change your DTEM period to a shorter interval, causing that phone to stay awake more often so it can receive the multicast calls if someone were to use push-to-talk. Hive APs can convert multicast frames into unicast frames to improve performance. The unicast frames are going to be acknowledged, which will create a little more overhead in the environment, but it gives you the opportunity to have ensured delivery. Higher data rates could also be used rather than using the lower data rates to support the multicast, thus improving throughput. Hive APs also perform IGMP snooping to check if any multicast group members are associated. Thank you for watching this session from Aerohive. Please continue the rest of the series at your earliest convenience.